Ford will give the next talk on first-order stochastic optimization.
So thanks, David. And I would first just like to start by thanking David for all of his work in this whole semester. I guess I'm an organizer, but I mean, David really is the organizer, and he did a lot of great work putting this together. So thanks. So first-order stochastic optimization is a big, broad, general topic. So of course, I can't talk about all of it in an hour or 2 hours or a week, maybe a semester. So what I hope to do here is talk about some aspects of stochastic optimization, more leaning towards those with applications in some of the deep learning problems that are omnipresent these days. Maybe throw out a few morsels to get you to see some of these problems from different perspectives, maybe focus on things like choosing the step size when you run stochastic gradient descent that I think are underemphasized in the literature in general. And I will focus in explaining more detail results that I was involved in, just because that's what I know the best. But if you see references during the talk, I encourage you to please go to those references, and also the references therein, which cite and which are cited by, to see the much bigger picture and all other results. So let's start with, in general, what is optimization in machine learning, say, today? Well, a lot of problems in large-scale machine learning are classification. We have a whole lot of data, maybe a lot of images, and we have a whole lot of data, and the data is labeled. So here, for example, we have a bunch of labeled data. The first row is airplane, the second row are automobiles, the third row is birds, etc. And what do we do with this? We want to use this data, run it through some black box, usually some optimization algorithm, which then produces some classifier, which, when then given image data in the future that is unlabeled, be able to automatically say, you know, what is the label of this data. So that sounds complicated, but often the black box that we put the data into to get out a classifier is an optimization problem that has this form. Minimize a so-called loss function, which can be written as the average of many component loss functions, and each component, little l, is associated with one of the labeled data points that we have. So say one of these images. Okay. So this is a general. I want to stress that this little n is a very large number, like in the millions. So this is a big loss function. Maybe 20 years ago, what would be a type of loss function that people could study with the computational power that was available then would be sort of what's a basic classifier, which is a loss function known as the support vector machine. In the simple case where the data that we have, the labeled data, has either two labels, say +1 or -1. +1 could correspond to the black dots and -1 to the white dots. We would want to find a classifier in the form of a vector w and sort of an offset scalar b corresponding to the maximum, the hyperplane that separates the labeled data, and does so in the best way, in the sense that it's a maximum margin separation. So the minimum distance to any of the labeled data points on one side or the other is as large as possible. So this would be support vector machine. Notice that here the loss function is nonlinear, but convex in this case. It's convex and can be written as in terms of a convex optimization problem. We have convex optimization solvers. And so if the data is not too large, we can just solve this type of optimization problem directly. Now, a more modern example of an optimization for machine learning is these so-called deep learning methods, where we still want to minimize a loss function, which can be written as an average of many component loss functions, but now each component loss function is extremely nonlinear, maybe taking the form of many, many products of taking a weight matrix, which is W1, W2, W3. Let's just say in this simple example, W1, W2, W3 are row vectors, and we want to optimize them. In each layer, we hit one of our row vectors, say W1, with the data point at hand, say X1. Then apply a nonlinear threshold, often a simple threshold where each vector, each component is thresholded to 0 or its component. So this is a so-called ReLU function in deep neural nets. And then this is repeated over and over and over. This is just 3 layers of nested products. But more often, people are using 50 layers or 100 layers of this. Okay. So this is very nonlinear. You have to sort of lay out an architecture of a particular neural network corresponding to the different layers and what is happening in each layer to try to explain how you go from the input, which is the labeled data, to a classifier. How can we solve an optimization problem of this form? Well, if you look at this function, it's very nonlinear, but it's possible to have an algorithm compute its gradient at a point. Compute the gradient of a function, capital F, using the chain rule. So when you have a lot of products of variables, you can use a chain rule, so we can at least write out what the gradient of the loss function is at a point. Anything more than a gradient is going to be difficult, and at the current state of things, not worth it in order to get a better optimization algorithm. So we're going to focus on first-order methods, which are iterative optimization algorithms which only use gradient evaluations and no higher-order derivatives to optimize a function. I hope I've convinced you that even computing a gradient of a function like this is going to take some work. And so I hope I've motivated the first order part of this talk. Yeah?
Q is a non-smooth function, but does the L really have a gradient everywhere?
That's a great question. No. But we're going to sweep that under the rug for this slide. Yes. It has a subgradient. But no, that's a great question. But for this slide, I'm just gonna sweep that. Okay. So we're talking about a first order method. We're going to just talk about the basic algorithm, which is gradient descent to start. Recall that if you have a smooth loss function, so a function that does have a derivative everywhere, then if you're at a point W, then greedily at that point, the direction that you want to go to, which is the direction of fastest decrease of the loss function, is the negative gradient. So the natural iterative algorithm is that's a greedy iterative way of trying to find a local minimizing point, or a point where the gradient vanishes, is to just go at each iteration some amount in the direction of the negative gradient, the loss function, until you've reached some convergence criterion, like the norm of the gradient small. So I want to say, because in this talk I'm putting some emphasis on the step size, this alpha j. Okay? In this setting of gradient descent, it's not so much an issue of what the step length alpha j is at each step. For gradient descent, in fact, there are line search methods which say that we can give you approximately the optimal value of alpha j at each iteration, which would be like the steepest descent, the one that really maximizes the amount of descent you have. If you say, I'm going in this direction, what's the best value of alpha? You can approximately get that optimal value in very, very cheaply using like a logarithmic extra number of derivative steps using line search. So that's not so difficult. What is a problem in these large-scale machine learning algorithms is the fact that computing even a single gradient of the loss function involves computing the gradient in the direction of the component function fi for all I from 1 to little n by linearity of the gradient. And little n is in the order of millions. So even computing this single gradient evaluation is not cheap. And it turns out that often it's the trade-off is such that it's worth it to instead do stochastic gradient descent. Descent in quotes because it's not necessarily descent deterministically, but rather an expectation. Stochastic gradient descent is instead of computing the full gradient of the loss function at the current iteration, which can be expensive, we're just going to randomly select an index among our n component functions, or select a small batch randomly of indices, compute the gradient only in the direction of that component function or that batch of component functions, and just go in that random direction at the ith iteration. So now we have a randomized algorithm. If we were to plot the iterations of some run of stochastic gradient descent, even if our loss function is nice and convex and has one unique stationary point that's a minimizer, stochastic gradient descent is going to get there in a bouncy, randomized way. And if we don't decrease the step size alpha j to 0, it's going to get into some well around the point and bounce around there forever. So if you want to converge for stochastic gradient descent, we have to take the step size to 0. We'll come back to that.
What was n and fi x again?
So n is the number of components if our loss function is written as an average of little n component functions.
And fi was?
Just the top here. So we're minimizing a function of the form capital F of x is equal to an average of little f I of x. And I haven't said anything more about what the fi are yet. Is that clear?
In the machine learning setting, can we think of it as the loss function on the ith sample?
Yes. In the machine learning setting, little f of I would be the loss function on the ith data point. So if you have a collection of 1 million labeled images, it's each of the image, you would do this. It's important that we draw a component function at random, or at least to understand why we do that. It's so that in expectation, at each iteration, we're going in the direction of the negative gradient. In expectation, the direction in a single component is an unbiased estimate of the direction of the full gradient if, just by linearity of the gradient, if we choose a direction at random. Yes?
So the topography of the space is determined by the particular training set that you have at that moment, particularly the sharpness of the basins and things like that.
Yes. Yes. So that is, let me talk about this. That brings me to a point I wanted to talk about in terms of the machine learning application. A decade or so ago, we would say, or maybe even more recently than that, it moves very quickly, that we're not really trying to completely optimize the loss function in machine learning because you just want to get a point that's close enough to the true, because what you really want to optimize is a loss function over the whole universe of data, which you don't have. What you have is just a subset of images out of the whole universe of images, say. So it's enough to just approximately minimize the loss function. And then that will generalize even better than if you actually minimize the loss function completely, which might lead to overfitting when then you evaluate your classifier on holdout data. So that was the perspective for a while, but now actually people in deep learning has moved towards over-parameterized loss functions. Over-parameterization means the number of layers in deep learning is so large that the variables, the dimension of the variable w that you're solving for, is larger than the amount of labeled data that you have, n. So you're solving an underdetermined system, in a sense. So now people say you really do in machine learning want to optimize the population risk, as they say. You really do want to go all the way to a minimizer of it. You're not going to overfit. And we're trying to understand why gradient descent and stochastic gradient descent methods seem to converge to a special solution among the infinitely many possible solutions, since it's underdetermined. Stochastic gradient descent seems to converge to a solution among the many solutions that has good generalization property, better than we understand right now. But that's a different talk. But I do want to say that I think it's really okay now to say that this is optimization. We want to optimize this function. Okay, so for stochastic gradient descent, in general, we're not going to get a result about deterministic convergence of the iterations to a stationary point or a local minimizer, because it's a randomized algorithm. So instead, we're going to have results about the, say, expectation of either the norm of the gradient, saying that goes to 0 at a certain rate, or if we have really nice properties, like our loss function is convex, strongly convex, smooth, then we might be able to say something about the expected value of the L2 norm discrepancy going to 0 at a certain rate between our current iteration and the unique global optimal solution. Okay. So if you look sort of at a survey of different theory for convergence of stochastic gradient descent, it's not very coherent, to be honest. There are lots of different results when you assume different assumptions about your loss function in your problem. And that's sort of bothersome, and it's not just a fact of that's just how life is, I hope. In practice, when implementing these methods in machine learning, there's really no rule for, in particular, how to choose the step size, alpha j, in stochastic gradient descent. And often one manually tunes this by hand for the particular problem at hand that you have in order to find the best values for this. And I'll get back to that. But a survey of some results are, if your loss function is smooth but not necessarily convex, then a certain carefully chosen value of constant step size, or step size decreasing like 1 over square root j, will give that the expected norm squared of the gradient of the loss function goes to 0 like 1 over square root j. If the loss function is convex, but not necessarily smooth, so it could have only subgradient, but not gradient, then again, a carefully chosen choice of step size decreasing like 1 over square root j allows you to say something about the expected distance of the loss function to its optimal value, going like 1 over square root j. If you assume stronger things about the loss function, that it's strongly convex and smooth, and each of the component functions is also convex, then a very carefully chosen step size value, constant step size, will give an exponential convergence of the expected L2 norm discrepancy up into a neighborhood of the minimizing point, sort of a neighborhood you reach a floor, where then you have to bounce around this neighborhood. And to see why you have to do that, if the step size is not going to 0, again, then you're only going to be able to get to within a certain distance of optimum and then bounce around. So we're going to talk about a couple of these different ones. So I first want to start with sort of the theory that's nice. Yeah?
The previous slide, C prime and C double prime, are they constants?
Yes, and that's not very good notation. They're actually like very constants that are carefully chosen to depend on like the noise level in the stochastic gradient, the variance. But they're definitely a constant and not something that's changing with j. Yeah?
Will you tell us how you choose alpha star? Is that another constant?
Yeah, that's another constant. Yeah.
The magic one.
Magic, yes, that's a great word. It is. It is. It's a magic one. So let me try to give you some more detail about the magic. Okay, so the setting where we have sort of the cleanest, shortest, most easy to explain, and probably most not illuminating, but shortest proofs of convergence are when we assume the most about our loss function. So if we assume that each of the component functions, fi, is convex, if we assume that taken together, then the loss function is strongly convex, and that each component function has a gradient, and that its gradient is Lipschitz continuous with Lipschitz constant L. Okay, so let me tell you, number 2 and number 3, just think of this as the Hessian of the loss function globally is upper bounded by some largest eigenvalue L and lower bounded by smallest eigenvalue mu. So basically we have this Hessian matrix, and globally we have an upper bound on it being L, and the smallest eigenvalue is lower bounded by mu everywhere. So this, you can understand why this is going to be really nice. It means that we can essentially turn this into a linear algebra problem where we have sort of a continuous family of linear algebra problems, but they're all uniformly bounded. So in particular, when we have a global upper bound of L and a global lower bound of mu on the Hessian, we can talk about the condition number of the optimization problem. The optimization problem has a condition number that, well, one notion would be L over mu. And then we can understand that the convergence rate should depend on the condition number of the problem. As we get better and better conditioned, as this number kappa goes to 1, the convergence rate should get faster. Yeah?
So when L and mu fixed, is alpha j also fixed, or is it going to vary?
Yeah, we're going to tell you a special alpha star that depends on L and mu that will give you great magical things. Yeah, yeah. And now another component that stochastic gradient descent will depend on, that say gradient descent would not, is something of the form of how consistent are each of my component functions and what their minimizing sets are. Okay, so in the case that we have strong convexity, that means there is a unique minimizing solution, x star, that we can talk about. And at that unique minimizing point, x star, what is the average value of the norms of the gradients of the component functions at that point? If that's 0, that means that the global minimizer of the loss function is also a minimizer of each component function separately. Okay, so that's really nice. That's a consistent system. So in that case, sigma squared would be 0, and we're going to have really good convergence. In the worst case, the component functions are saying we want to go to completely different sets of the domain when you go in this direction, stochastic gradient, versus this one. In that case, sigma squared is going to be big, and we're going to get confused, and stochastic gradient descent isn't going to converge as fast. So I hope I convinced you both of these things are sort of natural parameters that would affect how well stochastic gradient does.
Are they both related, or are they kind
No.
of, they're sort of...
They're not related.
So these are two separate sort of...
Yes, and I want to tell you let's look at the example of solving a system of linear equations. This is related to previous talks at this workshop. And all of these symbols that I'm throwing around, you can really place them in terms of linear regression. So if we want to solve a system of linear equations, so we have ax minus b, and we want to solve for x using stochastic gradient descent. In that case, each component function would just be the inner product of the ith row of our matrix applied to where we are, x minus bi, and then squared. Okay. So stochastic gradient descent for solving or getting a sort of least squares solution to x minus b would be pick a row of a at random, and then move in the direction of that, and then repeat, pick another row at random, and so on. So here we have that the Lipschitz smoothness constant from the previous slide is the maximum L2 squared norm of the matrix times n. The strong convexity parameter is going to be related to 1 over the norm of the inverse of our matrix squared, so that the condition number L over mu is close to the condition number of a matrix, except not quite, because it's L over the components, the component norms, rather than the whole matrix. And the consistency parameter is, well, this thing, which if our system of equations were consistent, if there existed a point x such that ax equals b, then the consistency parameter would be 0. Because ax equals b means that ai inner product x equals bi for each I. So any questions at this? Yeah.
For the strong convexity parameters, or like all the other ones have a factor n in them, is there a way to think of, is there an n associated with mu?
No, because mu is the strong convexity of the loss function as a whole. So the Lipschitz constant is depending on each component individually.
So if you look at the ratio of mu and L, which you do, right, then there's a factor n typically in there, or are those typically within a constant of each other? It looks like they should be off by a factor of n, which is enormous.
Yeah. Well, it's not, because if all of the rows of the matrix have the same norm, then L would be the Frobenius norm of the matrix. So it'd be the Frobenius norm squared divided by or times the smallest eigenvalue squared. So it's sort of like it's very related to the Gibbs number, but just Frobenius instead of spectral. Okay. Yeah.
So is x star the solution of the least squares
Yes.
problem?
X star is the solution of the least squares problem.
But that means sigma's there is always 0.
No, not if it's overdetermined.
That's the definition of the solution of a least squares problem. A transpose times the residual is 0 at the solution.
That's true, but this is individually AI transpose applied to AI. So you're doing it separately.
But isn't that capital A transpose times the residual?
No?
Little r is B minus AX star. A transpose R is 0.
I think what you're saying would be true if it was the norm of the sum, but this is the sum of
Yes. I agree with if this were out here. I think that's true. Yeah.
Sorry.
Yeah. No problem. Yes. Thanks for looking so carefully. This is all good. And I also want to say that if A is underdetermined, because that's very important too, that there is additional results where it says, okay, then mu would be 0, but we can still get convergence in terms of the minimal non-zero eigenvalue. Okay. So in fact, this, I guess in this talk, we're talking just right here about strong convexity means for a system of linear equations that the matrix is overdetermined. But actually, there's a way to get around that and also have the same thing for underdetermined system.
So
Yeah.
the bottom line, you just need absolute value. That's a scalar inside the norm, isn't it?
AI transpose is a vector being multiplied by a scalar.
No, but you're right. He's right that this is this doesn't have to be a norm. No, Justin's right that this is a norm. Thank you. Justin's always right in talks. It's kind of weird. Right? He's like yeah. Okay. Okay. So a theorem about the convergence rate of stochastic gradient descent, under these smoothness and convexity assumptions that I listed, is that as long as you have a step size that's constant, a constant step size alpha, as long as that step size is less than 1 over L, L you can think of as the Lipschitz, the maximal Lipschitz component of the component functions, then we get this decrease in the L2 norm squared in expectation. This is discrepancy to the unique minimizing solution that has these two parts. there's an exponentially decreasing part that decreases exponentially in j. So as you go along, we're going to exponentially decrease, but then there's a second term. That's a constant term that depends on the consistency parameter, sigma squared. So what this says is we're going to have two phases in stochastic gradient descent. We're going to have an initial phase when we're very far away from the minimizer, where we're going to converge very quickly, exponentially quickly if the step size is chosen correctly and we have these conditions, until we get to a point where the second term starts to dominate when we're pretty close to a neighborhood of the solution as given by the consistency parameter. And then our convergence rate is going to stall out when we have constant step size. Okay. And if the consistency sigma squared is 0, in the best case, then we just get fast decrease all the way to that solution that everyone agrees on. So everything's great. And as a corollary to this, we can actually do a calculus and solve for what's the optimal step size, optimal constant step size, to balance these two terms if we fix a priori a tolerance term epsilon. So we want to say I want to get to be within epsilon distance of the minimizer. Tell me what step size I should take. This step size results in this number k of iterations in order to get to a point which has expected L2 norm squared error less than epsilon. And so again, this k number of iterations depends on two things, the condition number. Okay, so if our optimization problem is well conditioned, this is close to 1, that's great. As long as it's bigger than the second term depends on how noisy our system is, how this consistency parameter. Okay. And I do want to mention that some history into getting this result started with a paper of Stromer and Verschinen in 2007 on Kaczmar's method for a way of, which is just stochastic gradient descent in the case of linear regression or solving systems of equations. And they came from thinking about these things, I think, as Ken was mentioning, Rudelson and Verschinen have their origins in high-dimensional geometry and convex bodies. So they took from that. And if you're wondering where we're going, the next thing we're going to sort of talk about is doing a sort of leverage score sampling in terms of sampling rows of a matrix or component functions in our sum of component functions in a non-uniform way in order to improve this convergence rate. And that was inspired by their paper.
So this is optimal, you said, or?
This is optimal, yes.
So is there an assumption that it's independent of j, or why isn't the step size sort of dependent on j itself?
So this is optimal in the setting where we have a certain tolerance that we want to get to. And then after setting epsilon, the tolerance, then we solve for a good constant step size in terms of getting to that point as fast as possible. Yes.
Okay.
Yes. Now, you'd want to decrease the step size if you don't want to preset a tolerance. Okay. So I'm running short on time a bit. So this is just to show you that the proof of this result is, this is it. It's just a few lines where we use all of the assumptions, the convexity, the Lipschitz smoothness, the convexity of the components individually. And it's just expanding the discrepancy between the point where we are and the optimal point at iteration k+1, expanding the square in a way to write it in terms of the discrepancy at the previous point, and then other inner products and norms, because then we want to use this to get a recursive inequality in terms of that. And now, because the conditional expectation, so if we say, well, we've gotten up to a point xk at iteration k, and now just thinking about the randomness involved in choosing a component direction at that point to move to the next point, k+1. So if that's our only source of randomness, so conditioning on that, and we take the expectation with respect to just the draw of which component direction we take at that point, then like the expectation passes nicely through all of these terms. This is the only random variable is the direction of the gradient that we take at that point. And so the expectation passes through, it's essentially linear, all of the terms, except for this last one, which we bound by the consistency parameter, in a way that then we get this recursive formula for the expected value of the error at k+1, given what the error is at k, and then we can apply the law of total expectation to get all the way back to a result about the total expected value of the discrepancy. And so as I alluded to, we can concoct simple examples to show that the convergence rates are tight, that we can't hope to do something better in certain situations. So for example, let's go back to solving a system of linear equations. Suppose that our matrix A is just this very overdetermined matrix where its first row is 1, 0, and all the other rows are 0 and then 1 over square root of n, where n is the number of rows. And we want to find the vector 1, 0. We want to solve for the unique solution 1, 0 to the system of equations A times 1, 0 equals 1, 0, 0, 0, 0. So if we run stochastic gradient descent with blind uniform sampling in this example, it's sort of stupid because with probability almost 1, stochastic gradient descent will pick a row 0, 1 over square root of n. And in case it picks that row, the inner product of that row, if say we start at, let's say we start at well, it's just going to project orthogonal to the solution x star. So the stochastic gradient descent update in this case is not going to move at all. We're not going to be able to move at all unless we happen to sample the first row, 1, 0, which will happen with probability 1 over n. So from that, you see that we're going to need an expectation, n steps. We're going to have to go through all of the rows in order to pick a direction that actually gives us any descent at all. So from that, we see that the Lipschitz, the condition number is n, and that matches that we're going to need on the order of n iterations. So in really bad examples like this, you can see how sampling and stochastic gradient descent from a different sampling components from a different distribution as opposed to uniform can really help. In this example, the first row of our matrix is vastly more important for the algorithm in terms of choosing that direction than any of the other rows. So we would want to choose that row with higher probability if in an ideal world in order to get to the solution faster. And this is a very artificial example, but in deep neural networks, there are classes of problems that are very unbalanced like this, in particular in like text classification. When you have labeled text data, there's no way to get around the fact that certain letters of the alphabet are going to appear more often, like E and T. They're going to appear more often than Q or Z. And at a higher level, certain words are going to appear more often than other words. And if those are your labeled data, then you're just going to have an unbalanced data set, and there's no way to get around that. And so some of the ideas here from this importance sampling are actually used when running deep neural networks in applications to text. Images you can normalize, pre-process easier, but text you can't really. So I'll just say for stochastic gradient descent with importance sampling, if we just were a little bit more refined and instead we look more carefully at each of the component-wise Lipschitz constants. So say each of our components Fi might have very different Lipschitz constants. Some might be much larger than others. The Lipschitz constant is like a curvature. How fast can the gradient of this component change as we move from x1 to x2? If it can change very quickly, then maybe we're getting more information from that component than if it changes very slowly. And maybe we want to sample that component with higher probability. Okay, so we might want to do sample non-uniformly. And we have to, if we sample non-uniformly, we have to then correct the step size in the direction of that component. We have to set the step size to be alpha over lambda I, if lambda I is the weight with which we draw component I, so that our stochastic gradient direction is still an unbiased estimate of the true gradient direction. So we're still trying to solve the optimization problem we have and not a different optimization problem. So important sampling and stochastic gradient descent also means you have to change your step sizes depending on which component or batch of components that you draw. And it turns out that a good choice of important sampling weights are to sample component I with probability proportional to the Lipschitz constant of its gradient divided by the sum of the Lipschitz constants of the components. 1/2 that and 1/2 uniform still. Or some other linear combination of that weighted distribution and uniform. It's important to have 1 part uniform distribution still in there because remember in stochastic gradient descent, the convergence rate depended also on this second term, this consistency term. And we don't want to mess that up. So in order to keep that second term unchanged and not a biased consistency term, we keep this.
So,
Ravi maybe, and then I'll get to you. Yeah.
so in the case of linear regression, right?
It's norm squared sampling.
Yeah, so length squared.
Yes, length squared sampling.
Square rather, it's Li squared, isn't it? Or
Li is the norm squared.
Li is a norm squared.
Yeah. Li, and I was going to mention that. So here Li is the norm squared. So this is the norm squared sampling that we've been talking about in the past couple of days. In the case of linear.
Right?
And Stromer and Verstinen were the ones to suggest that, and then we extended it from linear systems to finite sum of convex. Yeah?
Do we have experiments for this?
I have some experiments.
Does it really work well?
Yes. Yes, it works. It works. The experiments work just like the theory would say, but I'm not putting the experiments here because I don't like that the experiments use this carefully chosen step size that depends on parameters that in reality we're not going to have in advance. But just as the theory says, with these weighted sampling, the convergence rate can, in the worst case, be improved by a factor of n, in the sense that the convergence rate goes from depending on the n times the worst Lipschitz component to the average. Sorry. That's not true. From going the worst Lipschitz constant to the average Lipschitz constant. So like in this example I showed before, instead of needing on the order of n iterations of stochastic gradient to converge with properly weighted sampling, you only need on the order of 2 or 3. As long as with the important sampling, we're going to pick that first row with constant probability, and then we're going to be fine. So the convergence rate can improve by a factor of n when n is the number of component functions. And the experiments, this is reflected in the experiments. Yeah.
So is it the right thing to think of the 1 over 2n term as like a regularizer, or is that off base?
Oh, maybe. Yeah, I like that.
Okay.
Yeah. It definitely is hedging your bets. If you knew that your system was consistent, a consistent system, so you could just converge really quickly all the way to the solution, you wouldn't have to worry about the 1 over 2n. You just go fully, go fully there. But hedge your bets. Don't know which term is going to be more dominant in the convergence rate. So I'll just sample rows 1/2 according to one and 1/2 according to the other. Yeah?
So do you know if there are any results that choose sampling probabilities like adaptively, so during process?
Yeah. Yes, so that's what I wanted to talk about. What I wanted to talk about, let's see. So that's an important thing. As you know, I'm emphasizing here, I want these results to be of practical use. And so we can get a very large improvement in convergence rate if we know these LIs. if we know these Lipschitz constants of our component functions. So you're not going to know that a priori. So there's a natural question of, if you're in the setting, as in deep learning, where you actually go through all of your data several times. So in deep learning, you can think of it as, these days, being over-parameterized, so an underdetermined system of equations, a nonlinear version of that. And in the undetermined setting, you go through all of the rows more than once in stochastic gradient descent. So you should be able to learn Lipschitz constants as you go, okay? Because you're at least reading all the rows once. So the natural question is there a way to adaptively learn these LIs? Maybe start with uniform sampling, go through 1 pass, 2 pass, learn good, better sampling weights and step sizes, and then adaptively move more towards important sampling and end up with a convergence rate that's as close as it could be to as if you knew what the LIs were beforehand. Yeah?
So if I'm using this with mini-batch SGD, is the little n the size of the mini-batch?
Yes. If you're using this with mini-batch, then little n is the size of the mini-batch, and the LIs are like the spectral norm squared. The spectral norm squared of the batch, the matrix, the batch matrix. I'm pretty sure. I mean, it's yeah. And so I just told you this theoretical question, I guess. I don't know the answer. I think it's a good question. So there's sort of 2 questions. One is, can we, learn them in some sense in order to get a convergence rate, and then can we use them to match the sort of magical convergence rate as if we knew the LIs in advance? Yeah?
So is it still an open question how you should best learn the
Yeah.
LI?
As far as I'm concerned, it's an open question. There have been lots of work, especially recently, demonstrating that empirically there are methods for adaptively learning the Lipschitz constants so that when applied to deep learning problems, which are completely violate the assumptions of convexity that I had before for the theorem, the important sampling will allow the deep learning algorithms to converge faster without losing generality.
So
Yeah?
at least in practice, is there any hope to be like slightly less pessimistic and instead of like global Lipschitz constants kind of care about local Lipschitz constants or something?
Yes. It's not, whatever you said, I would argue that that's an even harder problem. Because what you really want is to move to do an important sampling that depends on the local Lipschitz constant where you are, rather than the global one.
Like gradient size or something?
Yes, because maybe you have a component function that has really high curvature off in La La Land that we don't care about, so its global Lipschitz constant is big, but locally it's something else completely. You want to use the local information. That's going to lead, theoretically that's harder. Yeah?
In theory, does something go wrong if you use a bad estimate, like an underestimate of one of these?
That's a good question. I forgot. In theory, if it's an overestimate, then it's a stable result in the sense that if you overestimate the Lipschitz constants by 2, there's just a factor of 2 worse in the convergence rate. If you underestimate, you're toast in some sense. So if you underestimate, then yeah.
So, maybe this slide answers this question, but I had the impression that that SGD sort of had a magical property in the sense that the generalization error is better than if you actually optimize the empirical risk exactly. And there are various kind of results of that nature that it's not convergence you really care about, it's generalization error.
So I sort of tried to allude to this earlier. That's, I think people don't believe that anymore. I think that was the belief until a few years. Last Monday. In the last few years, the deep learning architectures have become very over-parameterized, whereas they hadn't. So when you have an over-parameterized system and there are multiple possible exact solutions to your optimization problem, it seems empirically that you really can drive the population risk to 0 and you don't see any overfitting in your generalization.
They then drive to a minimum weight solution or something.
Exactly. So then the question isn't like whether we should solve the population risk exactly or approximately, or whether SGD is magical. It's why does stochastic gradient descent and maybe even also gradient descent, why does it converge to a minimum norm solution among the infinitely possible solutions? So that's the modern way of thinking about it. We can prove that it will converge, gradient descent will converge to the minimum norm solution when we have a system of linear equations, because then it's very trivial that you stay in a certain small subspace. You stay in the row span throughout all the iterations of gradient descent. Thus, it must converge to a sort of what do they say? Special, generalizable, nice solution, low complexity solution. So the question of how does that happen more generally for nonlinear problems is sort of where that is right now. Did that? Yeah. Yeah.
Speaking of implementation, are there any numerical issues that arise here? I saw some n's in the denominators.
No, there aren't, because the sampling weights are sort of, they're not bad. They're 1/2 uniform sampling plus 1/2 biased sampling. So you're never doing something very singular, like dividing by 0.
So in practice, you can say for current n's, throw double precision at everything?
Yeah. There's no dividing by some...
Or I should say, pay the price of double precision everywhere.
Yes. So just in the last couple minutes, I want to say that these questions of learning the Lipschitz constants, I think is really interesting. But there's even a more basic question that seems difficult, which is even without importance sampling, just uniform sampling, there's still only a certain range of step size, say constant step size, that will give you convergence at all with SGD. If you choose a step size too big, like greater than 1/L, where L is the maximal Lipschitz constant, then you won't converge at all. Stochastic gradient descent will bounce around and even diverge. So even without importance sampling, just plain stochastic gradient descent, choosing a good step size depends on knowledge of at least the Lipschitz constant of the problem, which isn't going to be known a priori. It's an interesting problem to say, can we learn it in a sort of one-pass way, in a streaming sense? Especially if all of the components have the same Lipschitz constant, you can imagine that that would be easier than if each one has a different one. So I just want to mention that this is sort of a current direction of research in stochastic optimization, to sort of making stochastic optimization less dependent on values of hyperparameters like the step size. How many of these parameters do we really need to set exactly in the magical way in order to get convergence? Can we put some dynamic update in the algorithm itself to learn some of these parameters? And so in particular, if you just want to learn the Lipschitz constant in stochastic gradient descent, then there are recent results showing that some very simple algorithms, which just correspond to embedding an update, sort of on-the-fly update of the step size or learning rate, just as a running average of norms of gradients that you've observed so far, or maybe norms of gradients you've observed in the last so few many iterations, can be used as an adaptive update to a step size so that you can get convergence rates for stochastic gradient descent with this update rule that are close to matching the oracle rates, which depend on choosing a step size carefully chosen depending on the Lipschitz constant. And this algorithm is called, is a variant of Adigrad. And so this is used a lot in practice in training neural networks with stochastic gradient descent. So it's not an algorithm that I pulled out of the air. These algorithms are used to make stochastic gradient descent less sensitive to parameters like the step size, and current results are giving theory for that. So I'm just going to stop there. It's time for lunch. Thank you. Yeah.
mentioned that important sampling was useful for data with text, but that for images you could normalize it away. Could you explain?
So for images, what they do currently is pre-process images in a training set. Pre-process the individual images in the data set to be sort of have the same L2 norm and same variance, which corresponds to essentially balancing all of the component Lipschitz constants to be pretty close to each other.
Wouldn't it depend more on the imbalance in your classes, though, with the training data? Like if you compared to that linear regression, you had one row that was different from all the other rows, wouldn't that be analogous to? It
might be. That's a good point. They also balance that. So in all of the standard data sets that people write machine learning papers on, like CFAR10 and ImageNet, all like the sizes of the different classes are very balanced as well. So now, just because people do this doesn't mean they should. Right? So I mean, what we'd really like is for a neural network to be able to take in streaming training data, not stuff that we've heavily pre-processed. So, so just because on the sort of standard data sets that people compare algorithms to, just because important sampling might not help on that doesn't mean that it isn't useful.
But you can't do the same type of normalization with like a word embedding or something?
No. No. Yes, sorry.
Here, instead of going over data multiple times and trying to learn all the Lipschitz constants, can you do something like metropolis testing or accept reject algorithm to just run it until it makes the distribution of the norm? You don't need to learn all the Lipschitz, you just run the Markov chain.
I don't really understand, but I like it. Maybe. If you think you know a way.
You start from some data point and then, let's say with Gaussian distribution, you go to the next data, and then you compare the ratio of norm of that one compared to this one. If it's higher, you reject, otherwise you accept, and then you show that it converges.
Oh, I see. So you say choose a component function and then stay on that component function, not just for one iteration, but for many iterations, so that you can...
At each iteration, you choose the next one, and then you decide whether you want to move or not. Okay? Comparing the ones.
Maybe. I should have added a caveat that in sort of the deep learning algorithms, they only do things that are pretty simple. They don't want to add extra stuff to the algorithms, because... so I don't know if maybe an accept reject, like line searches are very ineffective in the stochastic setting. So that's another sort of accept reject way of choosing the step size that they don't use. So I don't know.
Okay, let's thank Rachel again.